complex form of Fourier transform. So now we have studied that the Fourier integral representation of any function f of x is defined using this series. F of x is equal to 1 by pi integration 0 to infinity a omega cos omega x plus b omega sin omega x d omega, where this constant a omega is calculated using this formula integration minus infinity to infinity f of t cos omega t dt, and this integral b omega that is calculated from minus infinity to infinity f of t sin omega t dt. So now in order to calculate the complex form for this integral, what we can do, we want our integral to be in this form, e to the power iota omega t. So we have this formula that e to the power iota theta that is equal to sin theta plus iota, it is equal to cos theta plus iota sin theta. So this is the formula that we'll use. This is the Euler's formula. So we want our final series to be in this form. So that is the complex form of Fourier transform. So we have this cosine series form and we have the sine series form, which we have just covered. So next, how can we make this to the complex form of Fourier transform? The first thing that we'll do, we'll substitute this value of a omega here, this value of b omega here back into this expression. So our expression for f of x now becomes f of x 1 by pi I as such, then integration from 0 to infinity. In place of a omega we write integration from minus infinity to infinity f of t cos omega t dt and cos omega x as such, this as such, and then instead of this b omega we write this whole term integration from minus infinity to infinity f of t sin omega x dt d omega. Next, what we can do, next we can just we can take this term common f of t from this one and from this one and the integration. So this whole term and this whole term we can take it common, so we will be left with cos omega t cos omega x sin omega t sin omega x. So and what is this formula? This formula is cos of t minus x into omega. So this is the formula of f of x. So we have f of x as this quantity 1 by pi integration from 0 to infinity integration from minus infinity to infinity f of t cos t minus x into omega dt d omega. The next thing is that now we wanted our integral to have this form e to the power iota omega t form. So let's see how can we reach there. So here we have this expression. So we know cos t minus x into omega, that is an even function with respect to omega. So that means you can write
ma'am.
Hanji. So this cos t minus x into omega, this is an even function with respect to omega, we all know that. So what would be this expression? Integration from minus infinity to infinity the function f of t into cos t minus x omega dt d omega. This would be equivalent to 2 times of integration from 0 to infinity f of t cos t minus x into omega. And because sine, that is an odd function with respect to omega, so that means the integration from minus infinity to infinity f of t sin t minus x into omega dt, this would be 0 because this is an odd function. So this expression is 0, so we can take its integration, that would also be 0, and we can multiply by iota by 2 pi, that would also be 0. So why we have done this, we'll see this in a moment. We had this term f of x, so we can write this term as 1 by, now instead of this quantity 0 to infinity f of t cos t minus x into d omega, we can write 1 by 2 of this term, right, from this expression. So it becomes, this becomes 1 by 2 times integration from minus infinity to infinity f of t cos t minus x omega dt d omega. So this is equation number 1. Next we have equation number 2, where because sine is an odd term, we have this value to be 0. So now we can add up these two terms. So fx plus 0, it becomes fx, and on the right hand side we have 1 by 2 pi in both the terms, so I can take it common. Then integration is present in both the terms, so it is here like this, and then f of t, and then the value of this cos t minus x omega, which is here, plus iota times the value of sine t minus x into omega dt d omega. So this is what we obtain, because the second term eventually turns out to be 0, so it has no effect on this term. So now I have told you this e to the power iota theta, whatever theta value is there, we have cos theta plus iota sine theta. So this term becomes e to the power iota theta, right? And you can rearrange it a little more. So from here you can separate out this term e to the power iota t omega, and then e to the power minus iota omega x. So we have separated this term. So whatever is this value, integration from minus infinity to infinity f of t to the power iota omega t dt, we have called this to be c omega. So our final expression becomes 1 by 2 pi integration from minus infinity to infinity c omega as such, and then this value as such. So this expression where the c value is c omega is this value now becomes our complex form of complex integral representation of the given function. So next we shall see some examples. So if our function is given to be in this form, from minus pi to pi, function is given to be modulus of x, and at every other point it is given to be 0, then we have to calculate the complex form of Fourier integral representation, and moreover we will verify it using the Fourier cosine integral representation. So in the first part, we will first calculate the complex form of Fourier integral representation. The formula for this is this one, and the value of this coefficient is calculated through this formula. So firstly we will calculate what is c of omega. So c of omega, that becomes integration from minus infinity to infinity f of t e to the power iota omega t dt. So its value is defined in this interval from minus pi to pi, and otherwise it is 0. So we'll break the limits from, we have this limits from minus infinity to infinity, so we'll break it from minus infinity to minus pi, and then from minus pi to pi, and then from pi to infinity. So first integral it will be 0, third integral it will be 0, so we would only be left with this integration from minus pi to pi. So integration from minus pi to pi modulus of t e to the power iota omega t dt. So here we can perform the integration by parts. We can call, again we can break this interval because of modulus. So in the negative interval from minus pi to pi, the value of this modulus term becomes minus t, and from the positive integral from 0 to pi it becomes t. So this is the expression that we obtain. So we can now perform the by parts and we can solve it, take the terms common, and so from here we obtain at this expression. So now you know these two terms. One is sine theta, that is e to the power iota theta minus e to the power minus iota theta divided by 2 iota, and the second term is cos theta, that is e to the power iota theta plus e to the power minus iota theta divided by 2. So I can use its value as sine theta into 2 iota, so I have written it just like that here, and instead of this one I can write 2 times of cos of omega pi. So this is the final value of c omega that we obtain. So once you obtain the coefficient, we can substitute the value of c omega here. So this is the final exponential or the complex form of Fourier series that we have obtained. So similarly you can check it for the cosine terms. So I think that you can do by yourself. You can check the Fourier cosine integral transformation of the function. That will also come out to be this same expression. So I think it is clear to you all.